At this point, you have hopefully reviewed the problems involving resistors in series and in parallel. Many of our more complex networks cannot simply be solved by reducing them into simple series-parallel combinations. There are two main rules that are extremely helpful in handling more complex circuits. They were first developed by Gustav Kirchhoff, and hence they are called Kirchhoff's rules. These rules are not necessarily for our typical AP Physics B problems, but I find them very helpful to find the currents and voltages in our more complex circuits. The first rule is called the junction or point rule. It states that the currents that flow into a junction, in this case I1, is equal to the currents that leave the junction I2 and I3. Or it is commonly written in other textbooks that it is the algebraic sum of all the individual currents into a junction is 0. Means the currents that flow into the junction we would consider as positive, and the currents that flow out of the junction would be negative. And hence in this example, I1 minus I2 minus I3 is equal to 0. This rule is based on the conservation of electric charge. We're assuming that no charge can accumulate at the junction. Basically, what goes in must come out. If it helps, you can use the water analogy. Here we have, say, 1 liter per minute entering the pipe on the left, and here on the right side, let's say we have 1 liter per minute entering from the right side. Then what happens with the water that flows out? Well, you'll get 2 liters per minute going out of the pipe at the bottom. We saw this rule being applied with resistors in parallel. The total current I going into junction A was equal to the sum of the currents that go through resistor 1, resistor 2, and resistor 3. Or here's another water analogy. The water is brought up the steps, like as it goes through the battery, and then when it's dropped off, and the rate of flow of this mass will divide up into these two channels, so that the mass flow rate through this channel 1 plus the mass flow rate of this channel 2 will all add up together and add up to the total mass flow rate up here. Next, let's study the second rule, which is based on the conservation of energy. The electrical energy is conserved because we have a conservative electric field. Suppose we go around a loop measuring the voltages across each successive element. When we go around any closed loop, we find that the algebraic sum of the voltages will add up to 0. Now let's make a round trip, A, B, C, D, back to A, and add up all the different voltages as we go through this loop. When the electric potential increases or rises, like you're going up a hill, that is considered positive, and when the electric potential drops, like going downhill, that will be considered negative. As we move from point A to point B, the potential decreases by a value of negative IR2. Recall that Ohm's law states that the voltage drop is equal to I times R. It is a decrease in potential, hence the negative, because as we travel across the resistor in the direction of the current, we are losing electric potential. Well, back to our water analogy. As you traverse a resistor in the same direction as the electric current, you're going downhill. You're going down essentially a waterfall, and hence you're losing potential energy, and there's a loss of electric potential. If you were to decide to go uphill across the resistors in the opposite direction of the electrical current, then you would have an increase in potential. So, if you proceed over a resistor in the same direction as the electrical current, you will lose an electric potential that is equal to negative IR. If you traverse a resistor in the opposite direction of the current, then there will be an increase of electric potential of positive IR. Now let's continue going across our resistors as we proceed from B to C. As we go across B to C, we go across that resistor R1, and there is a potential change of negative IR1. By the way, I forgot to mention in this circuit that We should have noted before we even started this problem what the direction of the current is. Hopefully you realize that since this is the battery here, this is the positive and this is the negative. And current in this circuit will flow from the positive towards the negative. So here's the current I going through resistor R2 and going through resistor R1 and then up through the battery from the negative to the positive. So as we go across both of these individual resistors, we lose a potential of IR2 and another potential of IR1. And now we proceed from C to D. As we go across the battery, we'll find that we'll have an increase of potential of positive epsilon, known as the EMF. The EMF is counted as positive if you traverse from the negative to the positive. If you traverse the battery in the direction of positive to negative, you're going downhill, and hence you'll have a negative EMF. Back to our water analogy. Here, the little people act as our pump, taking water up to the top of the stairs and going from a low potential to a high potential. So, if you traverse a circuit from the negative to the positive, like you're going up the stairs, then you're moving to a higher potential. If you move over a battery from the positive to the negative, then you're going down the stairs and you're losing potential. I sometimes think of it this way. If I were to traverse a battery from the negative to the positive, I draw a little set of stairs out of my battery, and I imagine my little guy walking up the stairs going uphill, and hence there's an increase of potential of positive EMF. If I were going over a battery from the positive to the negative, then I imagine my little guy is starting at the top of the stairs and he's walking downhill, and hence he loses electric potential. And now as we continue our journey from A, B, C, D, and then back to our starting point A, we find that if we add all of these potentials, minus IR2 minus IR1 plus the EMF, and they will all add up to 0. This is consistent with the conservation of energy law, since all of the decreases in electric potential energy across these two resistors will be equal to the increase of potential energy across the battery. If we rearrange this equation, putting these two terms on the right side, we get the EMF equals IR1 plus IR2. And then if we factor out an I from each of these terms, we get the following expression. And hopefully you'll realize that the sum of R1 plus R2 is the equivalent resistance. And hence we can solve for the total current by taking the EMF and dividing by the total resistance, which is R1 plus R2. So in summary, these two theorems, the junction theorem and the loop theorem, can be used to solve complex single loop circuits as well as multi-loop circuits. Now go ahead and try the next few examples that deal with Kirchhoff's rules.